Hello and welcome back to Unconventional Computing. We are in chapter 4 talking about quantum computing. More precisely, we've started discussing quantum gates on our journey towards Shor's algorithm for integer factorization. So let's recall basic examples of quantum gates and then proceed how we can combine them to solve more complicated problems, very similar to digital gates, to Boolean gates and Boolean circuits, but with the underlying quantum realm. Let me share the slides. Right. So quantum gates operate on qubits, and qubits can be realized, for example, by ions trapped in an ion trap. And the important thing is that the way the ions are stored, um, they should maintain possible or created entanglement. So entanglement is a crucial key component to the efficiency of quantum circuits. And so we illustrate that here with a picture of six magnesium ions loaded into such a ion trap. And each ion is supposed to have a spin up or down modeled mathematically with a two-dimensional complex Hilbert space. So that's a four-dimensional real space. And we fix some orthogonal bases like 0, 1 and 1, 0, two-dimensional. And we abbreviate these two basis vectors with a 0 and a 1 in bracket notation. But observe that this 0 and this 1 is different. This is just a notational abbreviation for a two-dimensional vector. And one thing to keep in mind is the fifth axiom of quantum mechanics is that the time evolution, in this example of a pure state, is described by Schrödinger's equation. And Schrödinger's equation amounts to a unitary time evolution. So if we start with the state psi at time 0, then at time t, the state is described by multiplying the initial state as a vector in a Hilbert space with a unitary matrix in the finite dimensional case of Hilbert spaces, which depends on time. And here's an explicit formula for this unitary operator. It's given by the variation of constant formula, which you may or may not know from classical ordinary differential equations. It captures the Hamiltonian, in this case, with time dependency. That gives an important constraint for constructing quantum gates and quantum circuits, namely, they must be unitary, and in particular, they must be invertible. So all computation must be invertible, which is very different from classical Boolean circuits and Boolean gates, which of course the AND gate or the OR gate are not invertible. The NOT gate is invertible, but when we discuss quantum counterparts, they all must be invertible, unitary. So let's review some examples. Um, all quantum gates must be reversible. And the first is a NOT gate, which is simply the Boolean NOT gate extended to the quantum realm as a 2 times 2 complex matrix operating on this two-dimensional complex Hilbert space, namely one qubit space, one qubit. And you see why it's called NOT, because it translates the vector abbreviated with 0 into the vector abbreviated with 1, and vice versa. Another counterpart is the Pauli Z gate, also operating on one qubit. And here it leaves the 0 vector unchanged, and it changes the sign of the 1 vector. That's not something that is not possible in the Boolean case, right? But remember here we have real vectors, so we have a negation which is different from logical negation. Then there's a Pauli Y matrix, which amounts to like flipping 0 and 1, like in the NOT gate, but also scaling them with a complex unity minus I or plus I, and it must have opposite signs because remember it must be unitary. So please verify that this is indeed a unitary matrix, simple exercise. We also consider a phase-changing gate, which leaves the the 0 vector unchanged, but scales the complex 1 vector with some complex number of magnitude 1. It must be of this form to be unitary, and that's a phase change, and that's something we implicitly already encountered when we talked about polarization of light. So this can be regarded as change flipping X and Y polarization, and this can be seen as an example of creating circular polarized light from vertically polarized light and vice versa, depending on the angle of the phase change. So this angle phi can be anything between 0 and 2 times pi, for example. Afterwards, periodicity kicks in, and so these are examples of 1-qubit gates, and they can operate, for example, on the first qubit, or we can place the gate on a second qubit. The other qubits are not affected by a 1-qubit gate, which means mathematically we apply an n-bit operator where the other qubits are operated on with the identity matrix, 2 times 2 identity matrix, formed into a tensor product, n-1 fold tensor product for the remaining n-1 qubits, and 1 qubit is actually affected by any of these gates. And we can do that, of course, for any qubit in this qubit register here. Question for you. What happens, what is the phase change gate when we plug in the angle pi, meaning 180 degrees? Well, let's see. If we plug in pi, then according to Euler's formula, this evaluates to -1. And this is a particular gate which we already saw here. This is the Pauli Z gate, right? So the Pauli Z gate is the phase gate with particular angle. So we can kind of get rid of that. And now we proceed to quantum gates on 2 qubits and then to gates on more qubits. And remember that in the for 2 qubits, the state space is the 4-dimensional complex Hilbert space. And we use these abbreviations to abbreviate the four-dimensional unit vectors. So it looks like this is 2-dimensional, but this is a 4-dimensional vector, another 4-dimensional vector, and so on. And first gate we want to review here is the controlled NOT gate. Remember the NOT gate on 1 qubit. The controlled NOT gate is a gate on 2 qubits, which exercise a NOT inversion on the second bit, provided that the first qubit is 1. And so in terms of matrix, this amounts to this matrix, right? So if the first qubit is 0, then it's the identity matrix. If the first qubit is 1, then it's the logical negation matrix, the negation gate that we saw from last time. And we can confirm that with see how this matrix acts on the 4 basis vectors. And indeed, when the first bit is 1, then it flips, changes 0 and 1. Another gate on 2 qubits is the swap gate, which simply swaps the 2 qubits. And the matrix representation for that is here. So, and you can see that with how this matrix operates on these 4 basis vectors. And indeed, when both input qubits are the same, then nothing happens. But if they're different, then they're swapped. So that's why it's called a swap gate. And please double check that these 2 matrices are indeed unitary. Now moving on to gates on more qubits. Now we start again with a 1 qubit gate, namely so-called Hadamard gate. The Hadamard gate kind of mixes the 2 qubits. It creates an entangled state out of a orthogonal vector 0 becomes the entangled state 1, 1, and orthogonal vector 1 becomes the entangled state 1, minus 1. So this creates entanglement, and it's often used as the initial step in many quantum circuits to create entanglement, and that's why maintaining entanglement is so important for when we're trying to realize quantum computers and quantum circuits. And we can see that by how it acts on the 2 basis vectors, namely the first basis vector becomes this entangled state, and the other one becomes this entangled state. Note the square root of 2 is simply a normalization factor to make sure that the result is still a unit vector of Euclidean length 1. And again, please verify that this is a unitary matrix. And this is acting on 1 qubit, meaning that on the other qubits, again, we have tensor product of the identity 2 times 2 matrices. But now we're going to consider a Hadamard gate on 2 qubits, which is the tensor product, not the Cartesian product, but the tensor product of 2 Hadamard matrices operating on 2 qubits. And here you see the matrix tensor product, right? Here you see how it's expressed. Now the normalization factor is dividing by 2 instead of square root 2. And again, challenge you to verify that this makes this 2 times 2 matrix a unitary matrix. And on the other remaining qubits, let's say it acts on these 2 qubits, on the other remaining n minus 2 qubits, we still have identity operators. But no, there's nothing stopping us from considering threefold tensor product of this Hadamard gate, or fourfold or n-fold. And here you see this is an n-fold tensor product of Hadamard gates, which thus operates on all qubits. None of them is left untouched. And this one creates a entangled state from the initial, let's say, this orthogonal basis vector 0, 0, 0, 0. Remember that this is a n bit, but it is an abbreviation of a 2 times n-dimensional vector. And this gets mapped by this n-fold tensor product of Hadamard gates into the entangled state. Right, so here we have 2 to the n dimensions, and this is the normalization here. And this can be expressed in this way, that the 0 binary vector abbreviation gets mapped to an entangled state where each binary number from 0 up to 2 to the n minus up to 2 to the n excluding is represented with equal weight with this normalized weight. So this is a common first step in quantum gates to create such a thoroughly fully entangled state out of an initial non-entangled state. And then use that entangled state to perform many operations in parallel, harnessing quantum parallelism. So that's one example of a n-qubit gate, Hadamard gate. Next example will be a quantum Fourier gate. And as a preparation, let's recall the discrete Fourier transform, which is a purely mathematical transform. So the discrete Fourier transform on n-dimensional complex vector, let's say, takes this n-dimensional vector x with index running from 0, index j running from 0 up to but excluding n. And the output is a linear combination of these input vectors, each one with a different complex unit weight given by this exponential function with imaginary argument. So it's a purely imaginary argument that makes sure that this weight vector has magnitude 1, and we need to normalize by dividing by n. And the output is again a capital n-dimensional vector, which we here call y with index k. So input is x with index j, output is vector y with index k, running from 1 to n. And you may recall from mathematics that this discrete Fourier transform is indeed a unitary transform, which means we have a good chance of translating it into the quantum setting. And that's exactly what we do here. Quantum Fourier transform simply is the mathematical counterpart to that on this n-dimensional complex Hilbert space, operating on all n qubits. And we describe it again with a matrix describing how it operates on the basis vectors. And now remember that here we have 2 to the n basis vectors, which we denote, abbreviate with binary numbers in binary, k ranging from 0 up to but excluding n, where n is 2 to the small n. And the kth of these unit vectors is then mapped to the similarly weighted also unit vectors, which are here an index with j. So previously j was just an index and k was an index, and here we use that again as index to the basis normalized unit vectors. So that's a quantum Fourier transform, and it is unitary. So we can represent it as a matrix, and that matrix will then operate on this n-bit, small n-bit qubit entangled or not entangled state. And the result will be some other unit vector according to the axioms of quantum mechanics. However, there's a problem with this quantum Fourier transform matrix. This is an exponential size matrix, right? So this is a matrix with 2 to the small n times 2 to the small n. Now, that by itself is maybe not a problem, right? So it's an exponentially large quantum circuit, which is maybe not surprising, since here we have an exponentially large sum, exponential in small n, right? But remember, we also had the n-fold tensor product of the Hadamard gate would also have an exponentially large matrix, but this matrix would be of a very succinct form, namely it's a factor. It's a product of small n Hadamard matrix, tensor product of small n Hadamard matrices, resulting in an exponential sized matrix, but its description is very concise. And so that's the essence of designing efficient quantum circuits is to use gates and to combine them such that the resulting gate has a small description, although it operates on an exponentially large state space. And this is not possible in general, for any unitary matrix, but for the tensor product of the Hadamard matrices, it's true by construction. And it turns out that also the quantum Fourier transform has such an alternative, much more succinct representation. And that's what we're discuss now. This is still mathematics. So this is one way of expressing this quantum Fourier transform with an exponentially large sum. But it turns out one can rephrase that. This is one way of rephrasing that as a small tensor product with only small n fold tensor product of these combinations of just two qubits. Okay, each one with a different scaling vector here. And again, I challenge you, it's a nice mathematical exercise to do the calculation and to verify that this results in the same as here. It's basically repeated application of the distributive law, right? So yeah, repeated application of the distributive law. Um, yeah, you may recall, for example, Bini's formula with a binomial formula. That's also a repeated application of the distributive law, results in an expanded expression which is exponentially large. And this is, here we do the opposite. We're able to rephrase the quantum Fourier transform as in a succinct way with only small n tensor product. This is called tensor factorization, and as I do need to emphasize once again, this is not in general possible for any even unitary matrix of exponential dimension, but here it is possible, and this is why it's so important for efficient quantum circuits. So let's express that now in this how it operates on the binary basis vector with binary x1 up to x small n, and the result is this expression, which is again n-fold tensor product. And here we express the scaling vector, or more precisely the phase, and the scaling complex weight using this abbreviation. It's a way of, concise way of expressing things. And here we have a similar one, right? Again, please verify that this is the same as this to some mathematical exercise. And now we want to turn that into a efficient, that is a small size, polynomial size quantum circuit. And this circuit makes use again of this phase gate on one qubit, right? Particular version of this phase gate, namely where the angles phi are negative integer powers of 2. So 1 over 2, 1 over 4, 1 over 8, and so on. Because this is exactly what occurs here. Right? So it has this form. This is a phase change gate, right? This is another phase change gate. And we use that in our circuit as a controlled phase gate change. Now remember, we also already discussed the controlled NOT, which applies the NOT operation on the second qubit depending on the first qubit. And here we apply a phase change on the second qubit, depending on the first qubit. If the first qubit is 0, we do nothing, it's the identity. If the first qubit is 1, then we apply the phase change to the second qubit, and we apply it with this uh, small phase angle of the form 2 to the minus k, where k is going to be an integer. So k is going to be 1 or 2 or 3 or n. This is called controlled phase with a special form of the phase angle. And this is exactly what we use here. And if we now translate this mathematical formula into a circuit, then we arrive at this very circuit where we have the Hadamard gate. Remember, Hadamard gate on one qubit. Here we have a controlled phase, this one, right, with k equals 2. This is a controlled phase with k equals 3, k equals 4, up to k equal n. So each one applies this phase change to the second or to the third or to the n minus 1 or to the nth qubit, depending on the other qubit. Right. And then we do the same again here on the second row, and then we do the same again on the next, and so on. So this is again, I challenge you to confirm that this is this quantum circuit realizes this mathematical formula with all these tensor products here, and verify that this is a unitary gate, right? And here we see the first principles of quantum gates. You might remember or recall from classical Boolean gates that some Boolean operations, work simultaneously in parallel, and then they're usually oriented vertically, and horizontally they operate sequentially, the time axis. And in quantum circuits, the parallel operation amounts to this tensor product, like the Hadamard matrix operates on all qubits simultaneously, applies this Hadamard transform on the first qubit and simultaneously on the second, whereas multiplication of operators, which is usually denoted composition of operators, amounts to sequentially operating on qubits. And we can combine them easily because the tensor product of two unitary matrices is again unitary, and the composition of two unitary matrices is again unitary. So we can use these two operations to construct more complex quantum circuits from very small basic ones. And this quantum Fourier circuit that you see here is an example of that. Okay, so now we're already making big steps towards, remember, our goal is Shor's algorithm, but first we need to discuss the so-called quantum phase estimation. So let's quickly analyze that this circuit has quadratic size, quadratic in small n, and depth, which amounts to sequential time, parallel time is only linear in n. So this is a very efficient quantum circuit, although it operates, as always, on a state space of exponential dimension based on this tensor factorization. So that's polynomial. And now we're ready to talk about quantum phase estimation problem and quantum phase estimation circuits. Quick stop here. So let's first recall our framework of quantum circuits. So we have a n, or in this case an m qubit input state, and then we apply an m qubit quantum circuit, which corresponds to a unitary matrix of format 2 to the m times 2 to the m. So here's some input vector from the Hilbert space, and the output is another vector psi prime in the same Hilbert space. And for the quantum phase estimation problem, we're promised that the input vector is actually an eigenvector to this unitary matrix, right? Remember, what is an eigenvector to a linear transform? An eigenvector is a vector which where the result is a scalar multiple of the input vector. Now, if the linear transformation, if the matrix is unitary, then this means that the resulting vector's scalar multiple and the scalar factor is actually a complex number of magnitude 1. So it is a number of the form 2 to the e to the 2 pi I phi, and phi is called this phase. So the goal of the quantum phase estimation is, given such a unitary matrix, given such a circuit, and given such a vector, which is promised to be an eigenvector, determine the eigenvalue, more precisely determine the phase, the theta here, or at least approximate it. So this phase is a real number between 0 and 1, and the goal of phase estimation is to determine that, or at least to approximate it up to some guaranteed absolute error. This is the quantum phase estimation problem. And now that we have discussed the problem, mathematically this should be easy, right? We just apply the vector to the unitary matrix, and then can read off, maybe even just from the first coordinate, we can read off, if it's a non-zero coordinate, then we can read off what multiple is the first coordinate. If the first coordinate is 0, then we cannot read off, then we proceed to a different coordinate, right? But the thing is, this is an exponential size vector. This is an exponential size matrix, and doing that in a efficient way with quantum circuits, that's what makes the quantum phase estimation problem, on the one hand, challenging, and on the other hand, once we have solved it, it will be the key to Shor's algorithm for integer factorization. Okay, so with that motivation said, please stay tuned with me. We now discuss solutions to the quantum phase estimation problem. So here's a scheme of how we, the general framework of a solution. So with a solution, I mean, of course, another quantum circuit. But the unitary transformation, the circuit whose phase we want to estimate for this eigenvector, is not actually part of the input. It's going to be hard-coded into the solution circuit. So we're going to discuss solution of the phase estimation problem for a fixed unitary matrix U, which will be kind of like a subroutine in a program. We will hard code this circuit U into our solution larger circuit, and only the eigenvector will be part of the input to the solution circuit. And the solution circuit will hopefully approximate this phase up to absolute error 2 to the minus n, where n is an integer parameter that we can fix and choose in designing the solution circuit. And the solution circuit will probably apply this unitary matrix several times. And one thing to observe is that the composition of two unitary matrices, as I said, is again unitary, but now the phase of a double composition is twice. And if we have threefold composition, then it will be three times. Or more generally, if we have compositions of power u to the power of a, u to the power of b, and u to the power of c, then the phase will be scaled with a plus b plus c, where a and b and c are arbitrary integers. And now let's discuss the first attempt towards designing such a meta circuit for solving the quantum phase estimation problem. Why is it a meta circuit? Because, as I said, it includes the circuit for the unitary transform U and its powers building the solution circuit. So this is a quantum phase estimation meta circuit solving the quantum phase estimation problem for a given unitary transform U. And it will include U, and it will include powers of U, here third power or kth power, and then it will in turn have to be a unitary circuit so that we can actually build it as a quantum circuit. And yeah, as I said, the output will be an approximation up to n bits of this phase, which is a real number between 0 and 1. So we're going to need n bits after the binary point to output this approximation. And in order to output it, we first have to provide, remember, everything needs to be square matrices. So we first input an n qubit vector of zeros, and then the meta circuit should output an n qubit approximation up to error 2 to the minus n of this real number between 0 and 1. So that's what we're heading for. And this n-bit qubit approximation should be the closest to the real number. And we're going to denote that by y. So we scale it, multiply it with 2 to the n, and then round the real number to the nearest integer. This means rounding up or down to the nearest with ties broken arbitrarily at 1/2. So the output will be an integer y, which will be a small n-bit integer represented in this n-qubit output. So that's going to be our meta circuit that is supposed to calculate this approximation. And now remember that one of the so we're going to so we have two parameters, right? M is the dimension of the number of qubits of the input eigenvector living in a capital M dimensional Hilbert space, and we have n for the approximation quality living again in a capital N dimensional Hilbert space. So this state space will be a tensor product of these two, so it will have dimension capital N times capital M. Now remember, the fourth axiom of quantum mechanics is that the result of a measurement is inherently non-deterministic. It produces something, namely an eigenvalue of the operator with a certain probability. So any calculation performed by a quantum circuit, well, the quantum circuit applies some unitary transformation, but at the end, we're going to need to do a measurement, like looking in the box containing Schrödinger's cat, and then some random process happens during the measurement, and the outcome will be This is a symbol of the measurement, right? With a operator A, self-adjoint operator A. And so we cannot expect that the result of the measurement will be the number y here for sure, but the number y can only be expected to occur with some probability. So we need to, how to say, tune down our expectations a little bit and expect and hope for the quantum circuit after the measurement to produce this approximation, at least with high probability and high, as you may recall from randomized algorithms in the classical setting, it suffices to have some sufficiently large probability. Actually, we're going to achieve probability 40%. And if that's not sufficient, then we repeat the same process and simply take the majority using probability amplification techniques that you already know from traditional algorithms. So now we have set the problem and the framework with this quantum phase meta circuit. And now we can actually proceed to design the first such circuit. And this is what we're going to do next. So here you're going to see the first such circuit. This is the number we hope to output with high probability. And we introduce some abbreviation. Namely, this is kind of the approximation error, delta, which is can be positive or negative. But in either case, since we're rounding to nearest, it will be at most half the best approximation error 2 to the minus n divided by 2. So this is going to be important when we then analyze the error probability of measurement performed on our the result of our meta circuit. And as I mentioned, the first stage usually is applying a tensor product of these Hadamard transforms to create a entangled state where each possible basis vector occurs with same weight. And this is also the case here. So we apply this n-fold tensor product of Hadamard transform on this n-qubit initial state of only zeros, and thus creating n-qubit fully entangled state here to operate on in parallel. And then we apply so-called controlled U. Remember, U is our matrix and it's hard-coded into this. This is an entire circuit and it's going to be controlled in a sense that I will explain now. So we already saw controlled gates which operate on 1 qubit or here on m qubits, depending on the value of another single qubit. But here we use it to depending on the value of all n qubits here. Namely, what we do here is if the first n qubits encode the binary number k in binary, then apply the kth power of the unitary matrix U to the other m qubits. And we do that for any possible choice of k. So this is expressed by this sum here. Everything must be linear, right? Linear operation. And again, I challenge you to verify that this is a unitary transformation on n plus m qubit states. Okay. So here's another way of looking at this sum, namely when the input is the qubit with representing basis vector whose binary numeration is capital K, where k ranges from 0 to 2 to the n excluding. And if the other state here is a vector psi, then output with a vector psi applied to the kth power of u, which means apply u k times repeatedly, sequentially, and maintain, don't change the first qubit. So this is what's happened here. And then the result will be the new state, right? Should be psi prime here. And recall, since, right, so this, this is a unitary transform, the kth power will result in scaling this vector with this weight vector with a k-fold of the phase which we want to approximate. So we want to approximate the phase theta, and this one is an eigenvector of u, and therefore it's also an eigenvector of u to the k, but with eigenvalue the kth power of this, which is means k times the phase here. So this will be the result here. New vector psi prime, should I better call it? So that this will be the resulting vector, and then we're interested actually in the output of the first n qubits, and there's a formula expression for these first n qubits, which again you better verify mathematically by yourself. And you see how this is a linear combination. Actually, the estimated phase, the phase we're looking for, scaled with all possible choices of k, encoded as weights to the base vector number k for the first n qubits. And then we're almost there. Then we apply the inverse quantum Fourier transform, which is, remember, quantum Fourier transform is unitary, so it's reversible. It has an inverse, and we apply that. And then the result will be, again, a tangled state containing weights Cx to all basis vectors enumerated with capital X, ranging from 0 to 2 to the small n excluding. And here's the formula for this weight, a complex weight, which is given by another sum, exponentially many terms here with index capital K. And again, ask you to verify again that this is the correct expression. So this is a normalization vector. Here we see the difference between the current index x and the y, which is the quantity we want to approximate here, we want to calculate, and weight vector weights, which involve this delta, this error, which is exponentially small, fortunately. And then do the math and apply the axiom about the probability, namely the final measurement, which we then apply here, yields the desired value with a probability which is given by the absolute value of this complex weight vector squared. And again, some mathematical calculus, which is not the interesting, it is interesting, but not the central topic of today's lecture, shows that this is at least 4 over pi squared. Actually, when delta is 0, when the phase is a perfect power of 2 to the minus n, then the result will be the y with probability 1. But when delta, when we do have to do some rounding to get to a nearest integer power of 2 to the minus n, then y, the weight here, the probability becomes smaller than 1. And the worst case is when delta is equal to 2 to the minus n plus 1, and then it's 4 over pi squared, which is a little bit more than 40%. And as I said, this is good enough to then repeat this experiment, prepare the initial state again, measure again, and then take the majority using standard estimates in probability theory to get an arbitrarily high probability guarantee. So this is our meta circuit for the quantum phase estimation problem. It's a solution, but unfortunately, it's not an efficient one because remember, we have all these exponentially many terms involved here. We have here an exponential sum, right? N ranges 2 to the small n. And also we have exponential powers. The original unitary transform represented as a circuit embedded in here, right? But raised to the kth power, where k can be up to 2 to the n almost. So that means we have to, this circuit contains compositions of u capital K times, right? So power means k-fold product, product means composition. So we have exponential compositions of the circuit representing u embedded here in this meta circuit solving the phase estimation problem, and therefore it is not an efficient solution to the quantum phase estimation. So how can we make this efficient? To make it more efficient, let's look again at this expression for the controlled U sub-circuit here, which you see here. And let's try to optimize that. So there's no problem with a n-fold Hadamard gate. There's no problem with a Fourier, quantum Fourier inverse transform. We already know that there's factors, right? A tensor factorization, but this is the one we need to optimize, and that's what we do now, okay? And again, we use mathematics, trying to factorize this sum using kind of the opposite of the distributive law, and it turns out that we can do that basically by expressing k as in its binary representation, right? So k is an integer up to the 2 to the n, including. So it is an n-bit integer, and one can express this controlled power as a composition, right? So this represents composition, but only of small n-fold composition. Composition means sequential. Small n means small. Variant of using only powers of integer powers of 2 of the original gate, where this is now an abbreviation for controlled powering depending on only one qubit. So this means raise u to the kth power depending on the value of the lth qubit in the first n qubit. And if that qubit is 0, then do nothing to the psi vector psi. Nothing means applying u to the zeroth. U to the zeroth is, of course, the identity, does nothing. But if the lth bit here is qubit is 1, then apply the k-fold product, the k-fold composition of u to psi. This is right. Remember, this means sequential. Product means sequential, and tensor product means parallel. And using this formula, we can then arrive indeed at a meta circuit for the quantum phase estimation problem, which is exactly, remember here are the Hadamard gates. Here's the inverse quantum Fourier transform. Here's the measurement performed on the first n qubits, and the m qubit input eigenvector promised to be an eigenvector. And here we apply this controlled powers of u, but now only integer powers of 2 in the exponent. So this is a kind of first optimization, but we're still not there, because it still involves repeating and composition of u with itself an exponential number of times. So naively, this means we need to repeat the circuit of u, place it sequentially after each other an exponential number of times. So this is not still not a polynomial size quantum circuit, but fortunately, and remember that's our goal is Shor's algorithm. And in Shor's algorithm, we're looking at a very particular unitary transformation, which does admit a succinct form for raising to exponential powers. And this is where we're going to end today. So in Shor's algorithm, we're going to apply this quantum phase estimation meta circuit, but for a particular choice of u. And the choice of u, which I'll motivate later why it's this choice, is the one which operates on a, remember, m qubit state here, right? And let's denote by L. Let's enumerate the basis vectors of this m qubit Hilbert space with capital L ranging from 0 to m excluding, and the result of the unitary transform as it's used in Shor's algorithm is another base vector, namely the base vector with index L times A modulo X. So what's the L times A modulo X? I'll explain in a second. That's the case when L, the index of the input base vector, is between 0 and X excluding, and otherwise it just doesn't change the input vectors with index L larger or equal to X. Remember, we have capital M, 2 to the M of these base vectors here. And X, now what is X? X is the integer that we want Shor's algorithm to factor. So that enters here as a modulo. And as I said, I'm going to explain in the next session why this is of relevance. This is number theory. And also we have a A. A is an integer parameter which is promised to be co-prime to X, so have no factor in common in its prime factorization with X. If it has a factor in common with X, then we can simply classically do the GCD, the greatest common divisor algorithm, Euclidean algorithm, and thus find a non-trivial factor of X, right? If it's co-prime, that's the difficult case, and that's where we invoke the quantum phase estimation algorithm. And the good news is, if it is co-prime to X, then this transforming L into L times A modulo X, then this is this forms a group, right? Multiplying with a integer co-prime to X, that's forms a group, group modulo X, and this guarantees that the thus defined unitary transform is actually a unitary transform. Otherwise, it's not. That's the first. Yeah, that's why we're what we're looking at in Shor's algorithm and what we want to use the phase estimation algorithm for. And now back to the original difficulty that this is still exponential. But this particular form of u, we have an explicit expression for this powers of u that's just multiplying not by a, but by a power of a modulo x, right? So that's the property of modular multiplication, that we can first do the multiplication and then reduce modulo x, or we can first reduce modulo x and then do the multiplication and then reduce modulo x again. And this allows us to apply the classical repeated squaring in order to find a succinct representation of this power of u. We don't want to have u encoded in our quantum phase estimation algorithm repeated 2 to the k times, but instead we take the repeated squaring algorithm, convert that into a unitary matrix, and then this unitary matrix is going to be have not size 2 to the n, but it kind of factors again. So that's what we're going to look at more closely next time. For now, that's already enough. We've discussed quantum gates on 1 qubit, like Hadamard, and then on q qubits, like the controlled quantum gates, then n qubit gates, like the n-fold tensor product of Hadamard gate, which operates on 2 to the n basis vectors, but is given in a succinct way, namely as the small n-fold tensor product. We discussed the Fourier transform, discrete Fourier transform, and its quantum counterpart, which again naively involves exponentially many terms, but again, it factors as a tensor factorization to a succinct quantum circuit. And then we discussed the quantum phase estimation problem, and we discussed meta circuit, quantum circuit that involves the circuit whose unitary transform we want to determine the eigenvalue of, given a promised eigenvector. And we discussed the first solution, which again resulted in exponential size meta quantum circuit for quantum phase estimation. And then we found a more efficient one using the controlled unitary transform. And we saw why this is important and how we're going to apply that next time, when we then finally arrive at Shor's algorithm, or more precisely, Shor's quantum circuit for integer factorization in collaboration with discrete algorithms. We still need to perform discrete greatest common divisor calculations, for example, and we need the discrete algorithm to apply error amplification in order to improve the success probability from 40% to anything we like. So at the end, Shor's algorithm is actually a hybrid algorithm involving a quantum circuit, which we're going to design next time, and classical calculation controlling that. So that's all for today. Thank you very much for your attention, and please tune in next time when we complete chapter 4 on quantum computing with Shor's algorithm. Thanks and goodbye.